Hi, this is John Whitaker again for the Mathematical Analysis 2 course, and this is our second lecture. Last time we had an introductory lecture which we reviewed some of the material from our first course that we had, Mathematical Analysis, that would be pertinent to differentiation. And we ended that first lecture with the definition of differentiation, the derivative of a function, real value function, where the function acted on a closed interval from R. And we did an example of a function that had a derivative at a specific x value. Today, I'd like to start off with reviewing that definition of f being differentiable at a particular x value, and then seeing an example of where a function that isn't differentiable at a particular x value. Okay. So let us recall the following definition. It says let f be defined and real value on a b. For any x element of A to B, form the quotient phi of t given by f of t minus f of x all over t minus x. Then f prime of x equaling the limit as t goes to x of phi of t is what we define to be the derivative, provided this limit exists. Okay. In this setting, we're going to be talking about a limit. With limits, we've talked about limits in metric spaces. And so we're thinking about the metric being applied to R, the output, where the output values are, and this closed interval, which is in R, as both being our usual metric. That's the difference between real numbers inside absolute values. So let us look at an example. Okay. As an example, let f of x be defined as a piecewise defined function of 0 if x is greater than or equal to 0, and minus 1 if x is less than 0. And then what we claim is that f prime of 0 does not exist. Okay. Well, what we want to do is say, what would f prime be defined to be, even if it doesn't exist? It doesn't exist because the limit doesn't exist, but what is it defined to be? It's the limit as t goes to 0 of f of t minus f of x all over t minus x. Except our x's here are 0. So let me put those in. And that's going to be equal to the limit as t goes to 0, and f of t, let's see, that's f of t, minus f of 0, well that's 0, all over t. And so that's equal to the limit as t goes to 0 of f of t over t. Now, what we're claiming is that this limit doesn't exist. Well, let's suppose it did, hoping to get a contradiction. let's say it exists, and therefore equals to some number L. Okay. So that means if we're given any epsilon, so let epsilon greater than 0 be given, then by the definition of this limit existing, there exists a delta greater than 0. Let's call it delta sub 1, such that for all t elements of R, that's our input value, with 0 being less than t minus 0 being less than delta sub 1, then the absolute value of f of t over t minus L will be less than epsilon. Well, let us pick a delta equaling to the minimum between delta sub 1 and 1 over epsilon. So this delta is definitely less than or equal to delta sub 1. And so if it's less than or equal to delta sub 1, as long as t minus 0 is less than this delta, it will be less than the delta sub 1. And so what we get for delta sub 1 will also occur for delta. That is, so for all t element of R, with 0 being less than the absolute value of t minus 0 being less than delta, I'll write this down, then output will still occur. F of t over t minus L will be less than epsilon. Let's take a look at two particular t values which satisfy that their absolute value minus their absolute value is less than delta. So let's say note t equaling to minus delta over 2 and t equaling to delta over 2 both satisfy that 0 is less than t minus 0, which is less than delta. Okay. So, for t equal to minus delta over 2, what do we have? We have absolute value of f of minus delta over 2, all over minus delta over 2, minus L will be less than epsilon. Okay. Now, delta is a positive number, so minus delta over 2 is a negative number. And f of negative numbers, I believe, was minus 1. So what we have is the absolute value minus 1 over minus delta over 2 minus L will be less than epsilon. So that says the absolute value of 2 over delta minus L will be less than epsilon. Okay, rewriting this inequality is an inequality without absolute values. We get that minus epsilon is less than 2 over delta minus L, which will be less than epsilon. trying to solve for L, if we subtract minus 2 over delta from both sides, we get minus epsilon minus 2 over delta will be less than minus L, which will be less than epsilon minus 2 over delta. Solving for L by multiplying both sides of the inequality by minus 1, and then having to switch the directions of the inequality, we get the following. So we get minus epsilon plus 2 over delta be less than L, which will be less than epsilon plus 2 over delta. Okay. Now, since delta is less than or equal to 1 over epsilon, then that says that epsilon will be less than or equal to 1 over delta. So that says that 2 epsilon will be less than 2 over delta. Okay. So we have minus epsilon plus 2 epsilon will be, this should be a less than equal to, will be less than or equal to minus epsilon plus 2 delta. Okay. But we know that this quantity is less than L, which is less than epsilon plus 2 delta. So, we have minus epsilon plus 2 epsilon is less than L, which is less than epsilon plus 2 delta. So, epsilon is less than L is less than epsilon plus 2 delta. Great. Now let's consider the case where T is equal to delta over 2. Then we have the absolute value of f of t over t minus L will be less than epsilon. So this absolute value quantity becomes f of delta over 2 divided by delta over 2 minus L will be less than epsilon. And now, delta over 2 is a positive number. F of a positive number was equal to 0. So, this says that the absolute value of 0 minus L will be less than epsilon. So, that says that the absolute value of minus L will be less than epsilon. Thus, that says that minus L is less than epsilon to get greater than minus epsilon, or multiplying everything by minus 1, we have minus epsilon is less than L is less than epsilon. Okay, if we look here and here, okay, we see we get two contradictory statements about L. L's got to be bigger than epsilon, but L's got to be less than epsilon. These are contradictions. And so our assumption that led to this contradiction has to be false. Thus, the limit as t goes to 0 of f of t over t does not exist. It can't equal some number f. So f pawn of 0, which is what this limit was equal to, does not exist. that concludes this example. Okay, as a definition, we'll say given a function f defined on closed interval from a to b, we associate a function f prime called the derivative of f whose domain is the set of all points x in a to b such that the limit as t goes to x of phi of t exists. We say if f prime of x, or f prime, is defined at x, then f is differentiable at x. If f prime is defined at every point of a set E that's a subset of the closed interval from A to B, then we say f is differentiable on E. Now, we have seen an example where f was not differentiable, and that was the previous example that we did. In that example, that f of x was equal to 0 if x is bigger than or equal to 0, or minus 1 if x was less than 0. One thing that I wanted to point out was, again, that f prime of 0 does not exist. And I wanted to say note that f of x is not continuous at x equal to 0. Okay? That's one thing. Some examples that we'll look at where f is differentiable on a set E is that if f of x is a constant function, then f of x is equal to some constant b, where b is an element of R. Then, for every x element of R, f prime of x is equal to 0. And here again, we're using the usual metric on R, that is the absolute value. And so here's a proof of this fact. So it's an example, but it's also really a fact. It says, let f go from R into R be defined by where f of x is equal to b, with b being the element. Then f prime of x, by definition, is going to be equal to the limit as t goes to x of f of t minus f of x all over t minus x. But that's just equal to the limit as t goes to 0 of f of t is just going to be b, minus f of x is just b over t minus x. That's equal to the limit as t goes to 0 of 0, and that is equal to 0. That's an example of a function that's differentiable on R. Another example is that if f of x is equal to x, then f prime of x equals to 1. Here's the proof of that. We let f of x be equal to x, then f prime of x is equal to the limit as t goes to x of f of t minus f of x all over t minus x, which is equal to the limit as t goes to x. Now f of t in this situation would just be t minus f of x is x all over t minus x, which equals to the limit as t goes to x of 1, and that equals to 1. Now, most of the time we're going to be dealing with functions the way we define them on a closed interval from a to b. That's their domain. Something to be said about this closed interval. Note if f is defined from a to b into R, again, we have the usual method. That's what we're thinking about every time here. Then f prime of a is going to be equal to the limit as t goes to a from the right of phi of t, and f prime of b is going to be equal to the limit as t goes to b from the left of phi of t. This left and right-handed limits were something that was discussed in the analysis 1 course, and this isn't going to be something we're going to emphasize here in this course. I just wanted to let you know we can talk about derivatives at these endpoints through these types of limits. Okay, but we won't be too concerned about that. Okay. Next, I want to look at a fact, a theorem. Here's what it says. It says, let f be defined on a to b. If f is differentiable at a point x element of a to b, then f is continuous at x. So this theorem says if the function is differentiable at x, then it had to be continuous. And we're talking about a function defined on a closed interval, a to b, into the real numbers, and we're using the usual method. So that's what's involved in this theorem. So let's look at the proof. Okay. First of all, let's note that for any x, element of a to b, x is a limit point of a to b. And so the way that we're going to show continuity at x for f is that we'll show that the limit is t goes to x of f of t, if you will, is equal to f of x. Okay? All right, well, let's look at that. Now, the limit as t goes to x of f of t minus, let's say, f of x. Is equal to the limit as t goes to x of f of t minus f of x all over t minus x times t minus x. Those are the same. Now, the limit of a product is the product of limits provided everything exists. Well, this is equal to the limit as t going to x of f of t minus f of x all over t minus x times the limit as t goes to x of t minus x. And that is equal to f prime of t times 0. Okay? And so what we conclude from that is since, well, that's equal to 0, since the limit as t goes to x of f of t minus f of x equal to 0, then the limit as t goes to x of f of t must be equal to f of x. So since x was a limit point of a to b, f is continuous at x. Okay. So differentiability implies continuity, excuse me. And we saw an example where if you weren't continuous, you couldn't be differentiable. Okay, but just because you're continuous does not mean that you're differentiable. And I'd like to look at an example of that. Okay, let's look at this example. Let f of x be equal to the absolute value of x. Then f of x, or f prime of 0, does not exist. But f of x is continuous at 0. Okay. Okay, well, let's look at the f prime of x not existing. And so, so as proof, let's let f of x be defined to be the absolute value of x. And where we think we have the usual methods. Okay? Okay. So let's back up. Note, let's show that f is continuous at 0. Note, we will show f of x is continuous at 0. Okay, how can I do this? Well, we let epsilon be greater than 0 be given. We need a delta bigger than 0 such that for all x's in R with so continuity, with x minus 0 being less than delta, then f of x minus f of 0 will be less than epsilon. So we want the absolute value of x minus the absolute value of 0 to be less than epsilon. We want the absolute value of x to be less than epsilon. So that means we want the absolute value of x to be less than epsilon. That means we want the absolute value of x minus 0 to be less than epsilon. But we get to control this. So here we just let delta be equal to epsilon. Thus, f of x equal to the absolute value of x is continuous at x equal to 0. Now we want to talk about the differentiability at 0. Okay. Now, f prime of 0 will be equal to the limit as t goes to 0 of phi of t, which equals to the limit as t goes to 0 of f of t minus f of x, well here in that case it's 0, over t minus 0. And that's equal to the limit as t goes to 0 of the absolute value of t, well, minus absolute value of 0, which is just 0, over t, and that's equal to the limit as t goes to 0 of the absolute value of t over t. Now what we're going to do is that we're claiming that this function is not differentiable at 0. So we're claiming that this limit does not exist. Okay? But we'll prove that by contradiction. So suppose the limit as t goes to 0 of the absolute value of t over t equals to some number L. It exists equals to some number L. And we'll get a contradiction. Okay. So, for epsilon equal to 1/2, okay, there exists a delta greater than 0 such that for all t element of R with 0 less than the absolute value of t minus 0 less than delta, the absolute value of t over t minus L will be less than 1/2. Now, t equaling to minus delta over 2 and t equaling delta over 2 both satisfy that 0 is less than t minus 0 is less than delta. So for both of these t values, we're going to get that this inequality is true. Okay. For t equaling to delta over 2, we have the absolute value of delta over 2 minus L will be less than 1/2. Simplifying this, we have the absolute value of delta over 2, that's just delta over 2, over delta over 2 is 1. So 1 minus L is going to be less than 1/2. So, this says that minus 1/2 is less than 1 minus L, which is less than positive 1/2. Working our way to solve for L, this says if I subtract 1/2 from both sides, minus 3/2 is less than minus L, which is less than minus 1/2. Subtract 1 for both sides. So that says that 1/2 is going to be less than L, which is going to be less than 3/2. Multiplying by minus 1 and switching the sign, the direction, I should say, of inequality. That's what we get. And that's great. Now, for t equaling to minus delta over 2, we have the absolute value of minus delta over 2 over minus delta over 2 minus L will be less than epsilon. Well, the epsilon is 1/2, so I'm going to put that in. So, this says that the absolute value of this will be minus 1 minus L. The absolute value of minus delta over 2 is just delta over 2. This is a negative number, and its absolute value is negative of itself. And then we divide it by minus delta over 2. That's just minus 1. This will be less than 1/2. So, we have minus 1/2 is less than minus 1 minus L, which is less than 1/2. So adding 1 to both sides, we get 1/2 is less than minus L is less than 3/2. So minus 3/2 is going to be less than L, which is going to be less than minus 1/2. Thus, we have two statements. That is, previously, from when t was equal to delta over 2, we had still on the board on the right-hand side here, it's 1/2 going to be less than L was going to be less than 3/2, and we have the line above, which I'll rewrite. Minus 3/2 is less than L is less than minus 1/2. These, which are contradictory. Okay. Thus, the limit, let's just write it out. The limit is, in this case, the limit as t went to 0, the absolute value of t over t does not exist. So that means that f prime of 0 does not exist. Okay. So this was an example of a function who was continuous but not differentiable. But we know from a previous fact that if you're differentiable, you are continuous. Okay? And these are for functions that act on either the real line or closed intervals of the real line into R. That's what we're working with. Okay. The next thing we want to do is list a fact having to do with algebraic combinations of differentiable functions. And so here it is. Theorem says, suppose f and g are differentiable. Well, first of all, are defined on A to B and are differentiable at a point x element of A to B. Then f plus g, f times g, and f divided by g are differentiable at x. And we have the three following formulas. Part A says that f plus g's derivative acting on x is nothing more than the derivative of f acting on x plus the derivative of g acting on x. Part B is f times g's derivative acting on x is nothing more than f of x times g prime of x plus, then we have f prime of x times g of x. Part B is nothing more than the product rule. And part C says f divided by g prime acting on x. Well, that's going to be g of x times f prime of x minus g prime of x times f of x all over g of x to b squared. And that's the quotient rule. That's the quotient rule where we're assuming g of x, of course, is different from 0. We'd like to look at the proofs of these statements. Proof. Let f and g be defined on A to B and be differentiable on, or differentiable at x being an element of A to B. Okay. For part A, the addition's derivative acting on x is equal to the limit as t goes to x of, it would be f plus g acting on t minus f plus g acting on x all over t minus x. That's equal to the limit as t goes to x of f of t plus g of t minus f of x minus g of x all over t minus x. And that's equal to the limit as t goes to x of f of t minus f of x over t minus x. And I'll say plus, I'll rewrite this as g of t. Well, I'm running out of room here. Let me write it a little smaller. Plus g of t minus g of x all over t minus x. That's equal to, well, the limit of two things being added together is the limit of each one, provided each one exists. So let's see. Let's rewrite this limit as t goes to x of f of t minus f of x over t minus x plus the limit as t goes to x of g of t minus g of x all over t minus x. I have to make sure both of these exist, but they do, because this is nothing more than the derivative of f acting on x, and the second limit is nothing more than the derivative of g acting on x. And so that's our first part of this theorem being proven. For part B, product rule, note f times g prime acting on x is equal to the limit as t goes to x of f times g acting on t minus f times g acting on x all over t minus x. And that's equal to the limit as t goes to x of f of t times g of t minus f of x times g of x all over t minus x. What we're going to do is add and subtract the same thing from the tops to get the limit as t goes to x of f of t times g of t. And here I'll write down minus, I'll write down f of t times g of x plus f of t times g of x minus f of x times g of x all over t minus x. That's equal to the limit as t goes to x. Breaking this up as f of t times g of t minus f of t times g of x all over t minus x plus, well, let's make it, plus, here we have f of t g of x minus f of x g of x all over t minus x, which I'll rewrite as two limits plus the limit as t goes to x of f of t g of x minus f of x g of x all over t minus x equal to, okay, so we can pull out an f of t. So it's the limit as t goes to x. If I pull out an f of t, what I'm left with is g of t minus g of x all over t minus x, plus the limit as t goes to x. Here in the next quantity, I pull out g of x, and I've got f of t minus f of x all over t minus x. And now, this is a limit of a product. So I'll rewrite this as the limit as t goes to x of f of t times the limit as t goes to x of g of t minus g of x all over t minus x, plus, here, this again is a product, so it's the limit as t goes to x of g of x times the limit as t goes to x of f of t minus f of x all over t minus x. Okay, now we can rewrite this as the limit of a product is a product of limits, provided each one of these limits exists. Now it turns out, because of our definition of where f lives, and we're using the usual metric on R, that x is a limit point of that closed interval, and so we know that f prime of x exists. So that means that f is continuous at x, and so that means the limit as t goes to x of f of t is equal to f of x by continuity, times this part right here is nothing more than the definition of g prime of x, plus here, again because of differentiability of g of x at x, well, actually this is a constant. The limit of a constant is the constant. Okay, so we have that. And here, this is f prime of x. And so that's the product rule being proved. Part C, f over g prime acting on x is equal to the limit as t goes to x f over g acting on t minus f over g acting on x all over t minus x is equal to the limit as t goes to x of f of t over g of t minus f of x over g of x all over t minus x. Using algebra here, that's equal to the limit as t goes to x. This will be f of t g of x minus g of t f of x. I'm getting a common denominator here. All over g of t times g of x times t minus x. That's what I'm getting. Okay. That's equal to the limit as t goes to x of 1 over g of t times g of x. All that times exactly what we have, f of t times g of x minus g of t times f of x. And I'll rewrite that as the limit as t goes to x of 1 over g of t times g of x, and product, so times the limit as t goes to x. And here, I'll say this is f of t g of x, and then I'll add and subtract the same thing. So minus g of x, f of x, plus g of x, f of x, minus g of t, f of x. And that's what we have. Which equals to 1 over g of x times g of x. And that had to do with the continuity of g of x because of differentiability. Times the limit as t goes to x of f of t times g of x minus g of x times f of x all over t minus x. And then plus g of x, f of x, minus f of x, g of t, all over t minus x. And that's equal to 1 over g of x to b squared times the limit of the first guy, and I can factor out a g of x. Times f of t minus f of x all over t minus x plus, this is the limit, as t goes to x. Here I can factor out an f of x, and we're left with times, if you will, g of x minus g of t all over t minus x. Okay, this is equal to 1 over g of x to b squared. Here, the limit is t goes to x of g of x, that's just g of x. Here, the limit is t goes to x of f of t minus f of x over t minus x, that's f prime of x, plus the limit is t goes to x of x, that's just f of x. Excuse me. And here, the limit is t goes to x of g of x minus g of t over t minus x. I can rewrite that as the limit as t goes to x of minus. Well, let's just pull out the minus in front of the f of x, and that would leave a g of t minus g of x all over t minus x. And therefore, we get, this is all times the 1 over g of x to b squared. This ends up being g of x and f prime of x minus f of x, this is g prime of x, all over g of x to b squared. That ends that theorem, algebraic combinations of differentiable functions, and that ends this lecture. Thank you very much.